the only time I ever felt jittery.
A single topic.
It doesn't seem too much, it's just like,
I don't really know if it works or it just makes me feel better to have something to drink when I work. I always like to have something to drink when I work because if I don't, then I don't have to work.
so even I have water. Water is great, I love water.
A nice cup.
No,
Oh, it's
but-
nice to have.
Oh, nice. Let me check. We'll answer right now. You'll be all right.
Where chapter 15, you gave me validation of mirrors. I think someone already did.
I just
Two
think
weeks
they're
back.
good. I
So I
think
kinda
get
feel
like
like-
a little like poly.
Oh, it's like take on the
That's like what I got into.
like.
I think I just like.
What's your question here?
Here, I have a meeting.
And it is.
Here's that. Here you go.
Is this all of us?
I just had the
6, 7, 8, 9, 10.
It's a thing.
All right, I think so. All right, students,
It's like the tandems or whatever.
welcome to class.
I stopped at this.
I want to settle something about what drinks you should have when you need to feel more energetic. I mix 100 grams of table sugar and 2 grams of table salt into 400 milligrams of water. And I drink that every 40 minutes while running. And I also do it when I want to feel something. And if you do that for long enough, then your caffeine tolerance goes way down. And then if you really want to have fun, you can just do a bunch of caffeine after you haven't done it for a few months. Last time I did that, I gained synesthesia temporarily and started hearing colors, which was really exquisite. So the trick with drugs, right? Don't flatten the curve, right? Take all of the drugs you're going to have in your life all at once, right? That's the way you get the most experience, right?
Are we recording? Are we live?
Yeah, I recorded that. And my favorite drug is the Rust programming language, which I compressed into just 2 semesters for your sake of enjoyment. I will say, with the benefit of hindsight, not sure I'm going to be teaching Rust again, but that's okay. It's too late for you all. There's some action items. I think graphics was done. Graphics was due on Friday. Now that it's done, we can look back on it and be like, that was too easy, right? I should have required you to do CUDA, right? And I actually have, speaking of drugs, I have someone that can hook you up with some CUDA access. There's this thing called Orca? Y'all know what ORCAs are? That's right, it's the Oregon Regional Computing Accelerator, huh?
The screen reader?
There's an Orca screen reader? A screen reader.
Yeah, it's open source.
It's free and open source. Oh, it's from GNOME.
Yeah. It's
That's
open source.
cute! Oh, look! It's a little Orca. Okay, quote, any student, instructor, researcher in the Oregon region. What's the Oregon region? I'm guessing that just includes Vancouver. I don't know for sure. Do we have anyone here from Vancouver that wants to volunteer that information about themselves?
I'm from there, but I don't know. I don't know anything.
Is it part of the Oregon area?
I don't, like, yeah.
Yeah, so there you go, Vancouver.
Okay.
Anyone want to shout out Camas?
I used to live there.
Camas, yeah.
What the fuck? Yeah,
Okay.
I went there for middle school.
That's crazy.
Or we can go a little bit further upriver. Anyone heard of Bingen?
No Washougal shout out?
We can do Washougal. Yeah, that's okay. Yeah. Which I thought was Washigal this whole time, so that shows what I know. Anyways, I'm not from here. So, I'm thinking, this isn't related to class at all. I'm thinking maybe we get to do some CUDA next year. GPU accelerated computing. And also, y'all know how I'm like annoying Okay, I have to be more specific. You know how I'm annoyed about like using text editors and stuff? This is actually a remote server, so I can make you SSH into it. And if you figure out VS Code yourself, I guess I can't really stop you from that, but I'm sure not going to help you.
VS
right?
Code figures it out for you half the time.
That's the problem with VS Code, right? This is why when we're teaching CS 151, we should make people do the calculations by hand instead of using a computer. CPU exceptions are algorithmically interesting, but technically tedious. That's supposed to say tedious. I forgot how to spell tedious. I think there's supposed to be an O in there. I don't know for sure. This is the coding content this week is a direct lift from blog. The lab is posted. I'm going to go in there and change it from idiomatic Rust to non-idiomatic Rust before Wednesday. So if you're one of those people that likes Rust, you can go through it quickly. I've already taken some things out, Jimmy.
Okay.
But you know, because you have the source document. I will never use lazy static. That's stupid. Okay, it's not cool.
What are you
Okay,
using instead? Just static mute?
of course. We're dealing with hardware. That's what static mute is for. I don't agree with this thing that a static mute for a hardware interface is not idiomatic. That's
Oh yeah, that's fair.
yeah, right. Okay. So I've included a bit of content. So something that like this completely took me by surprise this week. I was like, there was stuff I knew about that I was making slides on that I knew about from my research that I did my like PhD in. That has never happened before. Like, I was a little surprised by that. So I'm actually going to make some references to things that I did in grad school, which will be fun for you because you're all planning on becoming computer science professors when you grow up. That's not true. Okay, you're going to become computer science professors when you're older without growing up. Okay, there we go. That was better. Okay. So you all know what the CPU is. It's the central processing unit. A lot less important than they used to be, folks. Everyone's coding GPUs now. No one really cares about the humble CPU. When was the last time you did a floating point operation? Hopefully never. Hopefully I got to you in time about those ones. I was teaching my AI class, and I had to use thirds for something. I was like, why didn't I just multiply everything by 3, right? Like, what do you need thirds for, right? Okay, so anyways, the CPU's hanging out, right? And every once in a while, you know how sometimes, this happens to me in real life too, someone asks you to do something that's impossible. Or they're like, hey Calvin, you can probably be in 2 places at once. And I'm like, probably not. And then they're like, the 2 places are Vancouver, Washington, and the Oregon region. And I can do that because it's the same place, right? I'm locked in. I can do it. So, but every once in a while, someone asks me to divide something by 0. Personally, the mathematicians never really got to me on this. I think dividing by 0 is totally defined. It's always infinity unless you're dividing 0 by 0, in which case it's 1. I don't know how this was so hard. Like, this was very straightforward to me. But I guess, like, computers don't know this, right? So for some reason, when you divide by 0 in a computer, sometimes it doesn't work. And this is humiliating for everyone. I just want you to know that my brain just triggered an exception because I realized I was going to write some code later, and so it triggered the launch Windows subsystem for Linux exception. But I'm currently on Linux, and the reason for that is because I was watching back my own videos last night. I was watching the one that I did on Windows subsystem for Linux when I left this computer in Portland. So I've been having nightmares about Windows subsystem for Linux, and I did that for you. I made that sacrifice. Okay, Windows subsystem for Linux, possibly the best Linux distribution. Don't say that at Linux user group. Okay, so what are we going to do? Dividing by 0 is like an obvious and silly example, but yeah, it's just like a little bit too easy to divide by 0 every once in a while. For example, depending on how you did the graphics assignment, you probably should have been hitting divide by 0s all over the place. If you were, sloppily indexing your arrays or something like that, right? The real more common one is accessing an invalid memory address. Rust is so annoying about this. They don't want you to just type in random numbers and then look up what value is at that address, because that is, quote, unsafe, end quote. Yes, we know it's unsafe, right? I understand it's unsafe. It's my computer. I want to see what is at that memory address. Okay, so all these things can happen, and mostly these things can happen, now, from the perspective of an operating system. Some other person perhaps, and I say these words with the utmost disdain, a software developer. Do you all want to boo for software developers? Oh, wow. Okay. Never mind, software developers are cool or whatever. Okay, so a software developer writes a piece of code, and perhaps that piece of code doesn't deal with all of its corner cases. And then you run that piece of code on your perfect, flawless, beautiful, immaculate operating system, which of course contains no divide by zero errors. And then the software developer's code has a divide by zero in it, right? Well, that's still your problem, right? Can never trust the software developers too little. So, anyways, this week, what we're going to do is we're going to implement an exception handler. We're going to do the absolute easiest possible one. Why? Because there's like a lot of exceptions, and they're pretty annoying. So we're just going to do a breakpoint exception. The breakpoint exception has the benefit of being really easy to invoke. So this is very easy to test. For those of you that don't know a lot of history of the breakpoint exception, it was invented at the Paris 2024 Summer Games. And I posted a link to the women's break-in final in the Discord, so you can go watch that. It's 13 minutes long. It features Japan's B-girl Amy facing off against Lithuania's B-girl Nikki, and it's superb, so I highly recommend you watch it. And that is relevant to this class. The purpose of that anecdote is so that you remember that things are called breakpoint. Okay, so don't forget that. Okay, meaning. Okay. An exception is when a bad thing happens while the processor is executing an instruction. Now, you all know instructions have been floating around for a while. Every once in a while, Jimmy tries to get you to write embedded assembly.
I've never tried to get anyone to write embedded assembly, except for Teddy Wilson.
Every once in a while, Jimmy's trying to get someone to write embedded assembly. Every once in a while, I'm thinking, why can't I just write embedded assembly? That happens a lot in this class. Probably all of you, because it's required, wrote serial print line, which uses the in assembly instruction, right? So you've all seen instructions. And what are they? Don't worry about it too much. It is a machine-level line of code. So not all of our lines of code refer to things that happen atomically, but some of them do. Plus is atomic. Most function calls are not. And at a lower level than the level of code we're writing, there is something similar to a notion of a line of code, which is just an individual assembly instruction. And any assembly instruction, within reason, can result in there being an exception raised. And most particularly, any of them literally can be interrupted by some other process. And a very obvious thing that can happen no matter what instruction your computer is running is someone can unplug it from the wall. This was a much bigger deal in the olden days when computers didn't have batteries in them, right? But it was commonly the case in early designs, and I mostly experienced this in the hard disk drive space, that someone can unplug a computer or a hard drive. The hard drive can detect it's running out of power, but it has time to execute a number of instructions. And so it did something, I think we didn't call it a blackout. It was either a brownout or a grayout. And you had some fixed number of instructions that executed at increasingly higher error rates. And what you did when someone hot unplugged a hard drive is it could get most of its internal state stable before it completely ran out of juice. And that was a pretty fun coding problem. So that's an example of something that can happen at any point in time, right? Someone can always cause you to run out of power. I don't know how this works with batteries. I don't know if they steadily decline in power over time. There's some critical threshold or something. I don't know. I don't know how batteries work. Does anyone know how batteries work? Okay. Find out how batteries work, let me know. Okay, so you're an innocent microcontroller controlling a hard disk drive. You're an innocent thermostat in a region that has rolling blackouts. You're an innocent laptop that is plugged into the wall and no longer has a working battery. An exception occurs. So what happens? The exception occurs. The CPU is going to pause doing whatever it's doing because it has something more important it needs to deal with. And what is it going to do next? That, dear reader, is up to you because you are designing the operating system. So the CPU is, no matter what, by hardware design, it is going to do something. And what it's going to do is it's going to ask the operating system what it should do next. The operating system can answer or not answer. The operating system doesn't answer, it has a series of fall-through steps, but in general, many faults are recoverable, or there are specific things we want to happen in the case of a certain fault, right? So usually, if we divide by 0, we don't want the computer to reboot. That is an overreaction. But we might want to terminate that specific executable, right? So you, as the operating system designer, have to make the decision of what happens when a divide by zero occurs. Okay. The OS manages these, which means you manage them. Okay, I think it's time for our first coding demo of the day. Let's see if I can set up my device. Has anyone caused any exceptions yet today? Oh, wow, that's a lot of code. Wait, what's plot.png? I can't load it?
That's the one you were messing around with. And then you changed the beginning of it.
Did I? Interesting.
Or you changed kind of it. I don't remember.
It's really hard to know. What's file.png? Here, let's see. Oh, that looks useless. Okay. I probably don't need URT-PHD either. Okay, so let's, why do I have a Pi cache? Okay. Temp. We got a variety of Rust here, probably. I'll just make a new one. We'll call it 0div. Okay. So, you all know Rust, right, by default. When you create a new crate, for some reason it gives you Hello World. And this seems so arbitrary, but I've spent so many years having C Hello World literally memorized and typing it frequently in front of class. So I guess I have to begrudgingly say it makes sense that this is the default state. Anyways, then we open main, and we can do a divide by zero. I'm going to print this one. I don't know that it's optimized out or not. I don't really know what Rust optimizes. The way to find that out is by playing around with it like we're doing here. So I'm going to take 1 and divide it by 0. Now, this is very important, okay? I got very confused why Rust was allowing me to divide by 0. My friends, I was dividing 0 by something. That is totally allowed. You are completely allowed to divide 0 by 1. That's just 0, okay? So make sure you remember how division works before you try and break your computer, okay? Because I could not figure out why it was just saying 0 when in fact 0/3 is equal to 0. So that made a lot of sense. They got me there. Okay, so this is 1 divided by 0, which is obviously infinity. Now what's the problem with infinity? It's symbolic. Computers can't count that high. Now, they can count that high using other forms of integers, but because in their infinite wisdom, our Rust language designers used the I32 type as the default for numbers. I32s cannot go to infinity. So this should cause some form of problem. So let's cause the problem. We're going to exit. Wait, no, I'm supposed to look to see if Indy's here. Indy's not here, but out of respect, we're going to do double Z. I'm going to clear this just so I have a fresh workspace. And then I'm going to, we'll look at it again. Okay, I'm just dividing by 0. Cargo run. What is this? What is this? This operation will panic at runtime? Error? My code won't compile? The Rust language is preventing me from allowing this to happen. And that sort of makes sense. Presumably you don't want to write code that causes your program to crash. But, I do want to do that. So we're going to go back in here. And I'm going to allow something. I think I'm going to allow an unconditional panic. Okay, I think that's fine. And then I can cargo run that. Wait, does not work? I thought that was allowed. Oh, the built-in attribute allow will be ignored since it's applied to the macro invocation. Right. Okay. So I have to. Let's see how smart I am.
You can just do it at the global level.
I can do that, and I'm going to do that by yoinking this line. I'm going to delete it. I don't know how to put open new lines ahead of something. Is there a graceful way to do that in Vim? I just did it manually.
Shift O.
Shift-O goes up? Okay. And then I have to insert an exclamation point here for this to be global. I can cargo run. Oh my goodness! Oh no! It's a panic. So, I'm pretty sure what's going on here. I don't really know how the Rust runtime works, but I'm pretty sure what happens is I tell Rust C, no, it's fine. Rust C generates the executable that contains the divide by 0. The Rust C created executable that divides by 0 is dispatched by the operating system. The operating system sees the divide by 0. The operating system incurs some hardware level error. Hardware level error calls an interrupt handler. The interrupt handler forwards things back to the Rust runtime. The Rust runtime gets a panic and attempts to do a stack unwind or whatever it is that the Rust thing does when it panics. It had to do something pretty sophisticated because it figured out what line of code the crash occurred in, so there was a lot of information being passed around here. And I suspect if I go into and I change my abort version, which I don't really remember how to do that. We say panic equals abort or something. Does that look right? Yeah, I don't know what that means. We fiddled around with panics earlier, and I think if you change the panics around enough, you are going to get not this. I'm guessing you will not get that back, but I don't know. Okay, so that's Rust. Rust, great language. We all love Rust, don't we? Okay, so there's also the other language, and I feel some obligation to show you this. So we're going to take a look at the other language, and I'm just going to do this in my same 0div directory, but I'm going to create some C files. So those of you that haven't seen C before, this should be somewhat intellectually interesting for you. So I'm going to make something, I think I'll call it main.c, because that's what I called it on the slides. We can start with the main.c boilerplate, which is, by convention, the C main function returns an integer. The Rust main function returns a result. Is that true?
It
It
can.
optionally returns a result?
Yeah.
Rust main returns the unit type.
It just returns
By
the unit
default,
type?
it returns unit type.
Okay. And the C main can optionally return anything. By convention, it returns an integer, so you can put an error status inside the integer. Why does it return an integer instead of a fixed size integer? Well, by convention, the error status is supposed to be in whatever the size of your device is, which is supposed to incidentally be the integer. It is also not uncommon for a C main to return nothing, in which case we would have void type, or just be unspecified and just say main. Those have fallen out of favor because I believe, and we'll check this in a minute, I guess, C++ requires, I believe, an integer return type. And so since C++ requires it, it makes sense to write the same return type for C. And in C, unlike Rust, we specify the return type prior to the function name. This is bad. Everyone hated this. Everyone in the universe hated this. And the first language I saw that fixed this was Go. I don't know if it was fixed before that. But it makes approximately 1 gazillion times more sense to specify the type of something after its name than before.
C++ optionally allows you to do that with modern versions too now, so.
Well, that must mean that C++ is a good language. Okay, so we're going to create an integer. We're going to call it x, and it's going to be 1 divided by 0. I'm going to do the thing that everyone hates. I'm going to put a space before my semicolon at the end of the line. This drives everyone crazy. I love doing it. I don't even know why I like it. I probably would have stopped doing it if it didn't annoy other people. Okay, and then we're going to return 0. Because 0 is the number of errors we have. And so if we successfully return 0 from this, we had 0 errors, and if we don't, then we had at least 1 errors. We'll go ahead and get out of here. Okay. The way I'm going to compile this is I'm just going to hit a GCC. We'll make this big. It's super annoying that... Wait, why didn't I just give my laptop a shorter name? That's what's taking up most of my space, right? I could just name it lap or LT. Okay, so we're going to GCC this. I'm going to GCC main.c, and I'm going to direct it to an output, which I'm going to name main. And when I do this, the GCC C compiler is going to let me know that I'm dividing by 0 and that this is not really encouraged. But it's going to let me do it, which I appreciate greatly. So I'm allowed to do that. And then I can execute the executable main, which will of course contain a divide by 0 and do something terrible. Okay. The point of this protracted exercise is I have in my life written a certain amount of systems code that contains absolutely no floating point numbers in it. Let me prove this to you. This is what main.c looks like. That only has integers in it, right? We only see integers. That took a long time to explode, by the way. Maybe we can time this. Like that is a very long time for a program that is 2 lines of code to run. And when it came back, it got a floating point exception. This is crazy. Okay, for whatever reason, most operating systems I work on, and I don't totally have a strong understanding of why this happens, pass back that you have a floating point exception when you do an integer divide by 0. There's got to be some reason for this that makes sense to somebody. It doesn't make sense to me. This is the least floating point exception you can possibly have. This is as far removed from a floating point exception as anything can possibly be. The weirdest thing that I've ever seen with this is this happened when I was working with pointers. I did some pointer arithmetic and still got a floating point exception. So I wasn't even working with integers. That was pretty weird. Okay, so this is one thing that can happen. So the C does not have a runtime that has a panic handler, that has a stack unwind, that has all of these things. It just gets obliterated by the operating system. That's your job, folks. You're responsible for hitting divide by zeros and printing out floating point exception. Okay, that's one thing we can do. Now, whenever we're working with C, it's always important to emphasize 2 different things. First of all, GCC is older than dirt, and so no one actually uses it like that anymore. It is much more common to use it with a series of flags. Here are my preferred flags. I have them here. Should I make a makefile?
No.
It seems like I should make a makefile. Okay, GCC main.c out main. I'm going to use wall, which is going to turn on all warnings. I'm going to use w extra, which turns on the additional warnings they added after they created the wall flag. I love this language. This is so cool, right? Okay. I'm going to turn on werror. That's going to take all warnings and promote them to errors. So things that are not even necessarily wrong with my code are going to prevent it from compiling. I'm going to turn on wpedantic. Why is that? Because I love pedantic errors. I recreationally write pedantic errors in my code and then have my code explode. I can't think of an example of a pedantic error right now, but that's okay. And then I use the O2 optimization level because that's what everyone else uses, and I succumbed to peer pressure. Okay. Oh no! If I use GCC but don't specify extremely silly defaults for it, then I can't actually still compile this. It's just like Rust, folks. All you have to do is know to provide all of those different flags. Wait, no, I forgot the best flag. Okay, I forgot the best flag. Sorry, the best flag is standard C89. Because you should never use a programming language more recent than how old you are. And this is the last version of C that's older than me, okay? So I use C89. Okay, so we should check a few other things. Do I type G++ or do I type GPP? I don't remember how to compile C++. I think that's allowed. I don't have it? Okay, never mind. Do I have Clang? Okay. All right, so that's how we do GCC. Okay, there are Clang fans. Okay, folks, that's not pronounced C-lang. I don't know why it's not pronounced C-lang. I am sure Golang, this thing, I don't know how that typing started there. Okay, Golang is like what runs Go, and everyone calls that, I don't think anyone calls that Golang, or Golong, right? But for whatever reason, the LLVM people are like, this thing's called Clang, not C-lang. I don't know why that is, okay? So don't trust them. But anyways, Clang is a drop-in replacement for GCC. It's promised to do basically the same things GCC does, but just have better performance. And those Clang people are filthy liars, and I'm going to prove it to you right now, because I'm going to compile a very, very simple program, and it's going to have different performance or different behavior in Clang and in GCC. And Jimmy's going to be annoyed about it, and then we're going to argue for like 2 minutes, and then we're going to move on, okay? All right, so everyone be emotionally prepared for this. Okay, so we're going to Clang main.c, and I'm going to call this one C main, because I don't know what else to call it. LLVM main? Clang main, okay. Okay, here's Clang main. Clang main, great. This is what it's supposed to do, right? That's a warning. We note that the warning is formatted slightly differently. That's fine. That's not a huge deal, right? We're probably seeing and teasing the beginning of the language conventions that ultimately turned into allow and deny, right? So this is in square brackets is a specific name of a type of error. I can allow my compiler to go forward with that error or to suppress that error or whatever I want to do, right? Those are just all in C. They work as compiler options, and they usually live in your make file instead of living in the code. I am opinionated that I don't think compiler directives should live in your code, but like no one asked me. Okay, so we made Clang main, and I bet, folks, it would be really weird if Clang main behaves differently than the exact same code compiled with GCC, the industry standard C compiler. Okay, so I'm just going to run it, and I'm not going to get mad no matter what happens. Folks, I'm super mad. There wasn't any error, and I divided by 0. This is very upsetting to me. And okay. I know it seems like I might be upset. I'm going to get more upset, okay? I'm going to check the error status that is returned by my main function. I'm going to do that by echoing something. I'm going to use a variable, so I'm going to look for something's nickname, and I'm going to use the question mark nickname, which refers to the return status of the previous executable. Folks, it returned 0. It said there's nothing wrong. It said there's 0 errors. So this code ran, and apparently there's nothing wrong with it, but it generated a compiler warning. So I know there's something obvious that we should do right now, right? We should see what it's actually returning. So let's go into source main real quick. Wait, that's Rust. I didn't mean to show you Rust in this class. I apologize. Okay, let's look at main.c. No, I can't spell. Help. Okay, I'm fine. Why don't we just return 1 divided by 0? And then we can take a look at it because we know how to look at return values now. Okay? So let's go ahead. We're just gonna get out of here. We're gonna pretend Indy's here. We're gonna double Z. And then let's just write out a little script that we can run more than once. We're going to make a Clang main. We're going to run Clang main. And then we also want to see the return value. $? Okay? And I'm sure this is going to be completely reasonable, and I'm sure I'm going to get infinity out of this, or at least in the absolute worst case, I'm sure I'm going to get the same number every time. Okay, if I don't get the same number every time, that would be extreme, right? Okay. Okay, so I get the warning and I get a 48. That's okay. So 48 is relatively close to infinity, right? It is closer to infinity than it is to negative infinity. So if we round, that's where it would go, right? And then if we do it again, oh, we're still getting 48. Okay, all right, I'm not mad. Okay, on my home device, I got different numbers every time. This is fine. Okay, Clang, saved. Okay, you're good in my book. Okay. Never mind, my entire demo didn't work. Okay. Clang doesn't trigger an exception. I do think it should explode. Okay, Jimmy, you had some things you wanted to share.
I mean, the warning it gave you is the reason why it's allowed to do that. Now, I don't know if that's necessarily good language design, but it is allowed to do that.
It's definitely allowed. I think I can also provide... I think Clang has all the same flags as GCC, right?
So,
So I can also cause Clang to behave the way I want it to.
yeah.
Okay.
Just how everyone uses it at this point, because of C.
Because C is awesome. Okay, so folks, you did not make a drop-in replacement for another compiler. If I can construct a 3-line counterexample that causes an exception in one compiler and runs without issue in the other compiler. Okay? That's not a drop-in replacement. You can't just use Clang for things, okay? You can use Clang. What are the things you're allowed to use Clang for? You're allowed to use it as your linker with rustc, and you're allowed to use it to compile Firefox, okay? All right. Isn't that all it's allowed for?
And it's really LVM that does that, not really Clang, I feel. I
Yeah.
feel like it's just that Clang passes that as a viable optimization to LVM, and LVM does some whatever optimization pass on it and gets rid of it.
Perfect. Okay. Now it is time to talk about exceptions, but first I have to look at my wrist. Okay. Are you ever sitting in this class and you think, wow, Calvin is exceptionally long-winded?
Yes.
Anyways, there's a lot of different types of CPU exceptions. In my defense, I shut up an entire day of the week. Right? Yeah.
Tuesday, Thursday.
Okay, I shut up 6 days a week. Okay. BlogOS would like me to introduce a series of different types of exceptions to you. That makes sense to me. So I lifted those exactly. I guess I feel like divide by zeros don't really happen that much. The real usefulness of teaching divide by zero and exceptions is it's something that we understand mathematically and is easy to invoke. I'm pretty sure you hit page faults more than anything else. I don't know if that's true, but that's my sense. What is a page fault? Well, a page is a chunk of memory. It's a strong claim to say it's a contiguous region of memory, but we model it as a contiguous region of memory, and it can be treated as a contiguous region of memory. And so every time you're looking up a memory address, it should correspond to some page in memory, right? It is, of course, possible to look at memory addresses that you're not supposed to look at, and the obvious way to do this is to cast a number as a pointer and then dereference the pointer. Should I do that? Oh, okay, we'll demo that. Do I remember how to do this? Okay, so probably don't need this anymore. Well, maybe I do. I don't think so. So we get in an unsafe block, because the entire point of this is to cause an exception. I'm going to take an arbitrary number, so let's say let adder shall be of type usize. We'll just do 1, 2. I should do some hex thing that is words. Code thing. 1, 2, 3, 4. Okay. So I take an arbitrary hex address. I'm assuming I'm definitely not allowed to look at this one. Seems like a safe bet to me. What do? Well, I am going to take that number, adder. I'm going to take it as a mutable, I don't know, U64. I like 64s. And sorry, I said mutable U64. That's not what I meant. A mutable reference to a U64. So I'm going to take that. I'm going to dereference it, which is super illegal, right? Okay, I'm looking at arbitrary contents in memory. Didn't initialize that or anything. I'm going to put a 7 there. 7, great number. Shouldn't offend anyone. And then what am I going to do at the end of my main function? I'm going to return. Okay, what am I going to return? I'm going to put a semicolon here, and we're going to see what happens. Okay? You know, I thought rustc was going to protect me, and I didn't get any compiler errors right before it hit a panic. I wonder if that has anything to do with the fact I put my entire function inside an unsafe block. That might be... I wonder if that's the same thing as turning off all of your compiler errors. Anyways, whoa, thread caused a non-unwinding panic. That's cool. I like that better. Multiple of 8. Oh, we can get a multiple of 8. Ah, okay, that's better. Okay, so Rust, I guess, just didn't let me use an... Do I say unaligned or misaligned pointer?
I always say unaligned, but I don't think it matters.
I think it's unaligned.
It says misaligned there, but
That's why I was thinking misaligned? Yeah.
yeah.
So perhaps we can only speculate here. This would be an aligned 32-bit pointer, right?
Yeah.
So it's not correct to say it's unaligned. It is incorrectly aligned for its size. Okay. So anyways, we'll Look, a segmentation fault. We got a segmentation fault in Rust, which I think you should always get an award for that. When do you most likely get a segmentation fault? I would expect this term, if you've seen a segmentation fault, it's when you have an arithmetic error related to writing to the VGA buffer. That's when I expect you will have seen this.
A couple people have that. Didn't say set fault, but it caused a triple fault and reset everything.
Yes, because if we're doing this in QEMU, we're not going to see that it's a seg fault. Yeah. Okay. Invalid opcode. You are aware that instructions exist. Not every piece of hardware has the same instructions, but every piece of hardware can be given the same code. That's possible. So sometimes you're giving code for hardware other than your hardware. When this happens, at some point in time, your hardware may be asked to do something that is not an instruction that it recognizes. When this happens, what else can the computer do but explode, right? Like it's just like you asked it to do something impossible, right? This is like when I get asked to be in the Oregon region and also in Boise, Idaho at the same time. Because as we know, okay, so I'm going to say something. Oregon and Idaho could totally be one state, right? That would be fine. Then we wouldn't have a hard border through the middle of the Wallowas, right? Okay. And then we could all summer in lovely Boise, right? I would like to reiterate, there are hella jobs in Boise, okay? Right, okay. The largest non-Korean manufacturer of computer memory in the world is based in Boise, okay? And non-Korean may matter in case there's like a tariff or something. Okay, so invalid opcode, pretty fun. Oh, yeah, okay, so I've seen these in real life, and when I'm used to seeing them was in early computer game design. Was using like accelerated graphics and all kinds of weird stuff all the time. And so there were all these games that were coming out that were commercially available that assumed unreasonable degrees of hardware development in the consumer hardware they were running on. So that they were hitting these opcodes all the time. Okay. General protection fault. There are regions of memory that exist that you are not allowed to look at, and the value of you here is a user running the instrument. Remember the software developers we were talking about before? Maybe the software developers aren't allowed to overwrite portions of your operating system that you wrote, right? And so those bits just live in memory, right? So something has to protect them. And the general protection fault is what protects them. So if there's an attempted write or read to certain regions of memory, the CPU has to raise a general protection fault. It will signal to the OS that the OS is supposed to do something. The OS will come in and take care of business, okay? This is necessary to make sure you're not constantly accidentally overwriting portions of your OS, rendering the computer unable to boot, right? Shows up in two other contexts that I think are really very interesting and more up to date. Virtual machine escape, which is a big deal in cloud security, and browsers, huge now, right? So browsers execute actual machine level code. JavaScript compiles into machine level under some level. That actual machine level code could potentially jump or look up regions of memory it's not supposed to go to, right? So there has to be a general protection fault boundary around whatever is going on in your browser. The double fault is famous. I think we accidentally just mentioned a double fault before we were supposed to. The way this was explained to me, I think it's very straightforward, and it is not literally true, but is close enough to being true. Sometimes something bad happens, and someone has to deal with it, which is you, the operating system. And while you're dealing with the bad thing that happens, another bad thing happens, right? And so you can incur an exception while you are still cleaning up from the last exception. When does this happen? Mostly, I think this happens when you have some sort of recursive error case, right? But it can happen in all kinds of things. So, for example, you can divide by 0, and we recall, when I divided by 0 in my C code, it took 1.18 seconds for the computer to recover. If during those 1.18 seconds I, for example, issue an interrupt command or a kill command to the executable in question, both of those exceptions have to be handled at the same time somehow. So someone's dealing with an exception and gets hit with another exception at the same time. Not a big deal, but certainly a common case of fault. The double fault is the fault of last resort that is dealt with by software. If something terrible happens while you're dealing with double faults, game over in some sense, and usually game over means the hardware is going to reboot itself. And this is a triple fault. So I'm dealing with a double fault. I'm sure I can handle it. There's no way things are going to get out of hand. Oh no, it's some additional fault. For example, I'm guessing I incurred a general protection fault while trying to look up a fault handler. Okay, so the operating system is now trying to shut down itself. You have probably seen this when trying to get QEMU to work in the first place. When there's anything wrong with our bare metal executable, I still don't like calling them binaries. If there's anything wrong with your bare metal executable, what will happen is QEMU will keep rebooting the system over and over again, attempting to boot successfully. Why is that? It's hitting a triple fault, powering off and powering back on, because that's usually the way you deal with triple faults. So triple faults are usually dealt with externally to the OS. The hardware turns off the OS and then turns the OS back on. Now, triple faults were come up with a long time ago in like ancient past, and the solution to everything wrong with computers is turn it off and back on again. And we still never remember this. Every time my electronics break, I still forget you just have to turn them off and back on again. So anyways, if anyone who works in IT has ever given you any advice, they're just doing the same thing as triple faults, and it makes sense to think of triple faults as an actual solution to that. Minimally, when you power the device off and back on, it's probably going to reset the entire working memory, and so probably whatever conditions contributed to the initial triple fault will not be there, unless the triple fault was caused by boot code, right? And if it's caused by boot code, then you have bigger problems to deal with. Okay, where do all of these things live? Well, someone, that's you, the operating system, has to put measures in place to deal with certain contingencies. And this is done with an interrupt descriptor table. I think of the interrupt descriptor table as a special case of a dispatch table. And a dispatch table is a table of functions. So how does this work? I'm the operating system. I bring my computer online successfully. I've brought my computer online successfully, and now I'm going to set up a table somewhere where I'm going to load functions into certain memory locations. These memory locations are going to be indexed by the numerical ID of different types of exceptions that can be given to me by the CPU, so that every time a CPU hits an exception, it just looks at that location in memory and then executes the code that's there, which hopefully deals with whatever problem the exceptions have. This isn't so bad. Now, we have seen something that looks an awful lot like a dispatch table before, and I'm just going to introduce a little bit of them. If you had the uncommon misfortune of having me as your CS151 instructor, I taught dispatch tables in that class. Everyone hated this. But I would like to point out that you can make Python a functional language if you want to, and I can prove it to you. So some of you may have some familiarity with the concept of key value storage, right? It's a recurring pattern that we've seen in this class. Okay, raise your hand if you've never heard of key value storage, right? No hands up, right? Great, we're doing a great job. Raise your hand if you've heard of maps. Not very many hands. Okay. What's something everyone's heard of? Raise your hand if you've heard of the 2005 Ridley Scott film Kingdom of Heaven. Oh, I was sure I'd get everyone with that one. Okay. I just found out Ridley Scott directed that this weekend. I've been on a real kicker for it. Okay. It features Edward Norton in an uncredited role if you're an Edward Norton fan. So just shouting that. Okay. So the keys are going to be exceptions. The values are going to be functions. So all I have to do to make a dispatch table is I create a dictionary, or perhaps a map. In this case, my keys are opcodes, stretching it a little bit, instructions perhaps, and then my values are, I used anonymous functions here. So I was teaching this in the context of the adventure assignment. The adventure assignment in CS151 is a text-based adventure game, which means people type something into the console. When you type something in the console and press enter, some action takes place. My line of thinking was a reasonable way to do this is to have a dispatch table that takes the command that is input to the console and looks up a corresponding function. So I taught students this version of the dispatch function in Python. We have seen something conspicuously similar to this, which is actually our test runner. You remember we had the term dynamic dispatch floating around? Well, that's just dispatch. So our test runner accepts a table of functions, and this table of functions is conspicuously similar to the idea of an interrupt description table. So we have already seen and we have already experienced in prior classes the idea of bundling up a bunch of functions together in some kind of linear data structure and then using it to solve some problem. In the case of the CS151 example, the problem we dealt with was actually interrupt driven. It was if some IO interrupt exists or occurs, we look up in the dispatch table what function we run, and then we run the function based on the interrupt. In the case of the Rust programming language, what we did here is whenever you're running your test suite, you incrementally look up different functions within your linear data structure of functions, and then you execute them in sequence. This is what my tester looks like. I don't know how far you are in testing this week. Oh, I have an announcement. I have no idea what the homework is going to be this week. Just be aware of that. I was sure something clever would come to me, and it hasn't. So the problem with homework for this week is like really exceptions aren't supposed to happen. So like most things I would have you do, you're just like not supposed to do them, right? Okay. Okay. So what do we have here? We have entries. Okay, in the interrupt descriptor table. This is a little bit weird, but just the one thing to point out to you about this structure, I wouldn't like particularly dwell on this slide, but it definitely contains function pointers, but it sort of splits up the bits of the function pointers oddly. So you have to sort of reconstitute the function pointer. You will have to check out some function pointer options. And you also have to find something called a GDT selector, which is, we're going to introduce a bit later this idea of a global descriptor table, which is a different table from the interrupt table, right? So there's all these sort of tables we're going to start pushing into memory when we set up our OS. And then we're going to be able to use those tables when some fault occurs or when we have to look up some memory location or any of the other things that our operating system has to do. One other thing I would like to point out to you on this slide that I think is quite relevant, there are 32 bits of reserved space in this hardware-defined, I'll call it a data structure. This is very common in systems computing. In the very early days of systems computing, when bits cost money, everyone was bit packing things together like crazy. Extensions became very difficult to implement. It is quite common now in modern devices to reserve large numbers of bits in any of your sort of potentially extensible data structures in the future. Now, in this case, we can look at this and we can infer something about it that should be interesting to us, which is that there are 4 things of size U16, which means that is 64 bits, and then there's one thing of size 32, which means we are summing up to 96 bits. So these 32 reserved bits, they incidentally are also exactly the size of buffer space we need to be 64-bit aligned. So I'm not sure how much credit people should get for forward thinking or saying reserved. What this is really saying is we have a 128-bit data structure of which 96 bits are defined. That's a fine thing to say, and I think that makes as much sense as saying U32 is reserved. I would be less convinced of that hypothesis if the reserved bits were in the middle somewhere. That would make more sense to me. This is the, oh no, am I cut off? Okay, we just barely cut that off, so it almost fits. There are 16 bits of options. What are these options? Mostly things we're going to deal with later, but we will introduce them a little bit. We have an interrupt stack table index. For reasons we will get to, sometimes you want to use a different stack space when an interrupt occurs. We have a few reserved bits. These bits I am more convinced are actually reserved because they're in the middle, right? Bit 8 determines if, when you are dealing with whatever exception you're currently dealing with, you will accept outside interrupts. So basically what this means is if something bad happens to the computer, it can stop listening to the keyboard or keep listening to the keyboard. Both of those options are allowed, and they're defined right here in the interrupt descriptor table. We have some hard-coded values. Oftentimes when we see hard-coded values, either they correspond to some legacy hardware implementation that needs there to be certain numerical values at those locations. But this additionally allows you to do one thing, which is every time you're looking at anything in the interrupt descriptor table, that if these values, bits 9 through 11 and 12, in every 16-bit options field of every single interrupt descriptor, if those are not 1110, you know some memory corruption occurred. This is quite useful because you can quickly validate that memory corruption didn't occur. Now, you're only looking at 4 bits, so maybe those bits weren't the ones that were corrupted. But if your memory is extremely corrupted, for example, if, you rubbed a magnet over your hard drive or something crazy, right? You would expect these bits to be wrong, and you would be able to quickly validate it. Now, we introduced last class the notion of the assert statement. Something that makes an awful lot of sense to me to do is every single time you have an exception, you should always assert that you see these 3 1s and 0, because that would be some way you could check to make sure you don't have memory corruption. Then we have something called the descriptor privilege level. The descriptor is just what we're dealing with. It is the 96-bit data strip. 96? What's 64 plus 30? Yeah, it's 96. The 96 bits that we're dealing with, and it has some privilege level. Now, on x86, privilege levels are 2 bits. To my knowledge, and I have looked into this, no one has ever used both bits. On every single executing x86 device I have ever seen, either both of the bits are 1 or both of the bits are 0. Why is this? The metaphor of having a super user level and a user level is a little bit too easy to implement. It is too useful. It is too convenient. Everyone just wants to do that. So most operating systems treat both of these bits as the privilege bit, where if it is 1, it is super user. Is that true? If it is 1, it is user, and if it is 0, it is super user, I think. I believe lower numbers are more privileged. The x86 designers expected people to want to use intermediate privilege levels between user and super user, but no one has ever come up with usefulness for any of them, so they only use maximum and minimum. Now, this should make sense to us because just in this class, that's not what I meant to do. Just in this class, we have seen these Unix level permissions. These Unix level permissions do not correspond to 4 different privilege levels. They correspond to user, super user, and then group. So you can still go up to 3. But in an overwhelming number of cases, at least 2 of these are the same as well, right? So every existing operating system that is used widely at all assumes there are only 2 privilege levels. Hardware supports up to 4. No one uses all 4. This is, perhaps unsurprising. I don't know what's going on with bit 15. I don't think it matters. Okay. Each exception, every type of exception, so everything that can go wrong with hardware, has some corresponding, we can think of it as an error code, right? Has some number. This number is defined at the time the hardware is developed. For example, on every x86 device, if an invalid opcode is detected, the CPU will look at interrupt descriptor table index 6 and execute the handler at that location. The same thing is true with page faults. Page faults are always at index 14. These numbers aren't meaningful, but they are guaranteed at the time of hardware development, and so they are massively backwards compatible and they can never be changed. Right? So, what this means is that once the operating system sets up the table, the operating system is not responsible for handling exceptions. The CPU, the hardware, will inherently run the code at those locations when some exception occurs. So your only responsibility as an operating system developer is to write the code that runs on exception. The hardware will enforce that it runs. Okay. Let's go through the steps of what's going to happen. You know, I was sure I checked that all of my slides fit on today, and I've had 2 different sizing errors. To pull the curtain back a little bit, I cannot get the same font in Firefox on my Microsoft Windows and on my Ubuntu Linux computer. Like, I'm not smart enough to do that. And it has something to do with me not caring about fonts at all and not trying. But it is still extremely annoying. So I'm annoyed. You are welcome to be annoyed as well. What's happening is this line did not overflow with the slightly narrower Windows font. And so that's what's causing this. Okay. So an exception occurs. What happens? Well, the first thing you do is you push a bunch of registers to the stack. Why do you do this? Every once in a while, here's how I think of this. Usually I get home before my partner, which means I'm writing super cool Rust code whenever my partner comes through the door, right? Which means I'm using 100% of my brain to remember 32-bit integers, right? Because I'm only using 32-bit integers. Now, when that key turns in the latch, all of a sudden I remember that I forgot to wash the only bowl we have in our entire house that has to be ready for either one of us to eat dinner as soon as we get home, right? And so, whenever the key turns in the latch, an exception forms in my brain, and all of the 32-bit Rust integers that I'm supposed to remember have to go somewhere. So what do? I do the same thing any other rational human would do. I open up a new Vim window and I write down all of the numerical literals, right? This is the exact same thing a CPU does, right? It writes down the numerical literals. It doesn't use Vim because it's a computer. It just pushes them onto the stack, okay? I don't have a stack because I'm a human, so I have to use Vim, right? So Vim stacks for humans, right? You're all sold, right? Okay, this is a great idea. Okay. And then what I can do, then I go quickly wash the dish, and since the lock on our apartment takes a certain amount of time to execute, I can always get the dish washed by the time the door opens. So I'm also very speedy. So a lot of people don't know that about me, that I'm quick. Okay. We would like to emphasize 2 different particular registers that are the most important. These are not 32-bit signed integers like the ones that I use in my brain when I'm writing Rust. These are good old-fashioned 64-bit values, except in the case of flags, which is actually used to be a 16-bit value. Then for a while it became E-flags and was a 32-bit value, and is now a 64-bit value, but the entire last 32 bits are not used. So the instruction pointer, it keeps track of the current machine-level line of code. So one of the things I always write down on my to-do list is what I'm supposed to do next. And for some reason, it's always answer an email from like one of you. I get a lot of emails, and I don't really ever want to respond to an email. Have you all ever felt this? Even if they're like really sweet emails. They're like, Calvin, we've nominated you for the Turing Award. And I'm like, I can deal with that tomorrow. So if any of you want to nominate me for a Turing Award, I'd appreciate it, but I won't say anything. Okay? And it's because I'm humble. Okay, so write down the thing you're currently working on. What is the flags register? The flags register deals with a lot of the current processor state, but I mean processor state in a very specific way, which is that it usually refers to the last instruction that the processor ran. So, for example, sometimes my 32-bit integers that I'm thinking about in my head, sometimes they're both larger than 2 to the 31st, and I add them together, which means my brain throws a carry bit, because I have to carry the numerical value over, or an overflow bit. And so whenever the exception is finally dealt with and we come back to the device, we'll have to know if we just performed an addition that caused there to be an overflow, right? Otherwise, we can't ensure the internal correctness of our numerical applications. So you push the flags register onto the stack as well. So you write down the next thing you were going to do and everything you need to remember about the last thing you did, right? I write that down, I push those registers onto the stack, and then I go on to step 2. But unfortunately for you, not for me, it's time for an aside. And the aside is we're going to talk about some hardware security. Okay, this is the flags register. So I want to actually physically show you the flags register, but I'm going to tell you 4 things about it first, and maybe this will make sense. The flags register keeps track of whether a carry has occurred, whether a value is 0. Why do you keep track of whether a value is 0? This is the most common. Most devices have a conditional jump instruction that jumps if the result of the previous calculation was 0. This makes a lot of sense if you've ever looked at a for loop in your life, right? So there's, I think it's called Jay-Z usually, which is, oh, that's also an artist, but it's spelled differently. I just unlocked myself. Hold on, I'm recovering.
You started talking about assembly.
I'm talking about Jay-Z.
Yeah, the assembly instruction.
Yes.
And also the ours, but
Yes. Okay. I'm not talking about assembly instructions. I'm talking about registers. So this, I think this is allowed because this is an architecture talk. Okay. With signed integers, there's something that says whether a result is a positive or negative, and there's also whether a trap occurs. We're not dealing with traps right now. This is what flags looks like. We have a carry flag, so we'll see we have different bits. You can hit the bits, the bits with different bit masks. The bit masks are provided and shown. Some of these things make more sense than others, but basically all of these flags are set every time you perform some kind of calculation. So, oh, maybe there was a carry, maybe there's parity, so whether the result is even or odd. I have no idea what auxiliary carry is. As far as I can tell, no one does either. No one else does either. We have something that says if we're 0. We have something that says if we're negative. We have the trap flag. We have the interrupt and enable flags. Remember when I was talking about how you can turn interrupts on and off? There you go. That's in your flags register. We have the direction flag. Do I have any idea what that does? No. No idea. I could look it up, right? We have the overflow flag. Huh?
I think that's the stack direction.
That's the stack direction. Okay, that makes sense.
I might be wrong on that, but that's.
I believe you. Yeah, we have the overflow flag. So obviously, you add 2 numbers together, you get back some result, but you don't know if an overflow occurred. And this is much more important with multiplication. There is the IOPL, which is the IO privilege level. This thing matters a lot. Come back to that. There's the nested task flag, which is no longer used. And there is the mode flag, which is no longer used. So some of these flags are no longer supported, and that's okay. All right. I used the R flags register in my research to get the doctorate that I do have that no one has asked to see. Okay? I think you can understand this sentence now. This sentence is listed directly from my research, though I think I paraphrased some things. When the in instruction executes, the IO privilege level, as given by bit 13 of the status E flags register. Why did I say bit 13 instead of bit 12 and 13? Bit 12 and bit 13 are always equal. In my research, I designed a parser that split up the R flags register by bit, and then it threw out some of the bits. So I only looked at bit 13. Bit 13 was always equal to 12. So I separately demonstrated that 12 was always equal to 13, and then I also demonstrated properties over 13, so I have properties over 12 by transitive closure. Okay? The IO privilege level must be greater than or equal to the current privilege level, which is called the CPL, and is given by bit 13 of a different register, the code segment register, which we're going to get to eventually. You know what the N instruction is. You've used the N instruction. You used it to do serial print. This is the only instruction we've used directly in this class, and it is referenced by name in a paper that I published, again, not fraudulently, and without falsifying any of my research. Okay?
Okay. You're very.
I'm just offended no one has checked if I falsified any of it, right? The reviewers were like, yeah, this looks fine, and like that was it. And it's like out there in the world. I poured my heart and soul. I spent 18 months working on that paper, and I think I understand it. Okay. So we've introduced the in instruction with the x86-64 crate. The current privilege level, we'll get back to this, but it came up in the context of the general protection fault. So if I'm executing at some current privilege level and I try and look up something that has a higher privilege level, I'm not allowed to see it. Not too complicated. We're going to return to segments, but I'm going to introduce them a little bit here. It makes a lot of sense when you have something like the instruction pointer or the stack pointer, those numbers don't need to be that big, right? So maybe only keep track of the lower order bits. And separately, maybe you have a lot of memory in your system, and so someone has to keep track of the higher order bits, right? So a good way to think of the segment registers is they tell you what big chunk of memory you're in, and then the lower order bit registers, like all of the pointers, they tell you the lower order memory bit. I think of this as what neighborhood you're in, or perhaps your street address, and then your numerical address, okay? This is a big performance win. Okay, back to work. Okay, step 1, exception occurs, CPU throws a bunch of stuff onto the stack, because you might need it when you get back. Step 2, we're going to look at the entry in the interrupt descriptor table that corresponds to whatever the code is that we got from our current exception. So if a page fault occurs, I read the 14th entry. Okay, I don't think that one's too complicated. 13, or step 3. I don't know why I said 13. Oh, I'm thinking about bit 13 of the I'm still thinking about bits, folks. Never start thinking about bits, you'll never stop. Okay, so push the registers on the stack. I read the corresponding entry. The corresponding entry is a function. I'm going to start executing the function. But before I can start executing the function, I have to make sure there is an actual function there. Because if there is not a function there, which is fine, that's allowed, right? The operating system doesn't have to deal with a contingency for every case. But the CPU is going to assume there's some function there that it can run. But if there isn't a function there, then you have to raise a double fault, which is a different type of exception, and then this thing runs recursively. Okay, I want to point something out. I have been mean to Rust this term. Rust has mostly deserved that. But this is the perfect case for the Rust option type, right? A potentially available function. That's a function object, which is already like an extremely Rusty thing to do, right? And it's enclosed in an option. So Rust is the correct language to implement this specifically. It's not for a different reason, but we'll get there. Okay. Check entry or raise double fault. Then you are going to potentially, but not necessarily, disable hardware interrupts. What does this mean? Well, some interrupts deal with internal state of the computer, and they have to be dealt with before you can take input from the user again, which means you can't look at the network and you can't look at the keyboard. Not all faults are like this. Sometimes we just don't care. Sometimes we're just dealing with a divide by zero error, and we can let the user keep typing, and it'll probably be fine. It'll probably work itself out. Right. So some exceptions are going to turn off the keyboard, and some of them aren't. You have probably all experienced this, where sometimes there's things wrong with your computer where you can keep typing, and sometimes there aren't. Those are simply the two types. This is implemented with the terminology using gate types. Basically, when some sort of exception occurs, it can happen because of what the CPU is doing, or it can happen because of something that happens to the CPU. In either cases, these events become visible to the CPU because it has to know someone's trying to deal with it, or that its internal state is falling apart. And this comes in through a gate. A gate is very, very similar to the idea of a wire or the idea of a register, but we're going to specifically use the term gate here because it's not really like this is a register that always currently has a value. It's sort of just a wire that is activated or not. I think of the two kinds as being like traps. So a trap is where I'm running some code, a bad thing happens, and I like place a cage on top of it, and I'm going to come back and deal with it later. This is like, so I'm taking my little cat to the vet, right? I need to trap her, so I like place a little, usually the laundry basket. So I put the laundry basket on top of the cat, and I can do that like several minutes before I have to take her to the vet, right? So if I see her and it's like we're leaving for the vet in 6 minutes, boom, laundry basket, like toss some treats in there, and I can like put my shoes on or something before I come back and get her. So that's the case of a trap. And then there's interrupts. Interrupts are completely different. That's if I'm not planning on taking my cat to the vet, and my cat like knocks over a building. I don't know how that would happen. My cat eats large cat unsafe plants semi-regularly. Like, do you all know what a monstera is? They're like big and have like the leaves, right? So those are not cat safe, and my cat loves to eat the monsteras, right? So sometimes there is an interrupt, which is where I hear a chomping noise coming from the living room, and I have to quickly write down all of the I-32s in my brain, and then I have to run out to the living room and pull my cat off the Monstera, right? So that's an interrupt. That's not where I'm placing the basket on top of the cat. So interrupts preempt other hardware interrupts, but exceptions do not. So while my cat is inside the laundry basket, she cannot chew on the Monstera. I don't know if that made sense, but it made a lot of sense to me, and I think that's important. Okay, so here's what happens. We have our first 4 steps. Some registers go on the stack, read the entry. The entry's not there, we double fault. We might or might not turn off hardware interrupts. And then what are we going to do? That says GDT for global descriptor table. Sorry, I was covering it with my mouse. You're going to take something out of the global descriptor table that corresponds to the current exception, and you're going to put it in your code segment. We should think of this the same way as just changing what the next line of code you're going to run is. When we put something in the code segment, that is the code that we are going to run next. The GDT is, I don't think it's too exciting, but it's, it's like the neighborhood map of the different memory regions you have. Within the neighborhood map, there are code segments and data segments, and those of you that are big fans of the Harvard architecture are eating really good right now, because what is this? We're differentiating code from data again, folks. It just happens to be in the same memory space. But there's separately maintained code and data segments. And there's all these things called system segments, which we're not going to worry about. The code segment is pretty cool. The code segment, we recall, it's bit 13 includes the current privilege level, so that tells you whether you're the supervisor or not. There's some other stuff in there. And then there's also 16 bits that refer to your memory region. Before an exception occurs, the code segment can refer to possibly anywhere. There is no restrictions on the possible values that the code segment could have. Why is that? Well, one of the things you're allowed to do is a page fault, which means you try to execute code arbitrarily located, right? So you can attempt to jump to a location that does not exist, which means anything can potentially be in the code segment. Now, as soon as the exceptions start running, the code segment's going to be restricted to wherever the operating system keeps your exception handlers. Okay. Whew. I've been talking a lot. Posture check? Is everyone staying hydrated? I'm not. Getting dehydrated. Yeah. I think I should become a wellness influencer. As everyone, how's everyone's knee and ankle mobility? Yeah, right? Like, I'm trying to bend my knee right now, and it just hurts, and I don't know why, right?
My knee doesn't even work right now.
Yeah. I think knees are overrated.
I agree.
I think we could get around with just our hips and ankles if we had to. Okay. All right. So the code segment, it contains memory addresses and some other information. That's kind of little. Is that too little? It was bigger on Windows. That's all I'm saying. Okay. Okay. Why do my fingers not work? Okay. Okay. So this is a segment descriptor. It does not only have to be the code segment descriptor. It can also be the data segment descriptor. It can be the SS. I think it's the stack segment descriptor. And then there's, on x86, there's 3 extra descriptors, which is hilarious, E, F, and G. And they're used for whatever you want, which is a crazy thing to say your hardware is for, right? There's a variety of bits in this thing, but it includes basically a series of address locations. I'm pointing at, and I will point my mouse at it, there's the DPL descriptor privilege level. Notably, that is at location 12 and 13. There's a 12 next to it because it's 0 indexed, so however you want to think of that, right? And these other things are kind of interesting too. We'll just go over this quickly. You should know what the code segment is. Ah! Okay, the F12 is right next to the F11, okay? I think we were on 55. Okay. DPLs are important. I think I already said that. Okay. So these are the steps when an exception occurs. Registers on the stack. Look at the IDT. If there's nothing in the IDT, panic. Potentially turn off hardware interrupts. Then in 2 steps, you get ready to go do some code. You change your neighborhood, and then once you finish changing the neighborhood, then you grab the handler function and you start running the handler function. And by the time you've done that, you know the handler function exists. Okay, handlers. I thought about this for a minute, and I was persuaded by blog and also by thinking about how annoying this would be to do. We don't really have a strong benefit to making our own IDT from scratch, as in from bits. So it is not completely unreasonable to reach back into the x86-64 crate for this. And I will begrudgingly admit at this point and no earlier, it is nice to have the x86-64 crate. Okay. It comes with something called the interrupt descriptor table struct of the x86-64 crate. And I want you to look at this and understand why I didn't want to write it myself. Okay? Do you see this? That is more text than I have ever written in my life. If I could write that much text, I would simply be a novelist. I would write Frankenstein fan fiction, probably. Is that true? That's probably true. Do you all know what Warhammer 40K is? I think that's the one that would get me if I were a writer. Like, I've thought about it a lot. Okay. I know this looks long. Oh, no, there's also a scroll there. And when you scroll down, so you additionally have to scroll down. And when you scroll down, it says, oh, this is only part of it. So that's how much nonsense there is here. Did I look this thing up at all? Absolutely not. But did I get extremely annoyed by one thing? Yes. This is represented in C because the internal Rust representation is not acceptable for operating systems. So I'd just like to point out the good programming language has shown up again. Okay. We're moving on. Okay. These fields all have type entry. See? It is of type entry, handler function. We'll see that there's a couple different ones of these. So divide by 0, famously easy one to deal with. And then we have page fault, famously difficult one to deal with, which actually has its own handler function type, the page fault handler func. And then general protection fault, which is one of the scarier ones, right? Because that means someone's breaking the rules intentionally or otherwise. That's an error handler func with error code. So are these likely encoding? So these are going to have different return types, right? So we have these 3 different types: handler func with error code, and page fault. We're just going to look at the handler func because it's easy. And folks, that is still a lot of text. Look at that. Okay. So this is a function. You can tell because we have fn here. It is a function that it takes an interrupt stack frame. What's an interrupt stack frame? We'll get there, but basically this is going to be a data structure that contains the stuff we need, right? But what is this? Xturn x86 interrupt. That is a Rust foreign calling convention. We've used this with start, I think. We use this in a few other places. So we usually use xturn for compatibility with C. That's not what we're doing here. Why are we not doing compatibility with C? The interrupt descriptor table is accessed directly by hardware. It is all the hardware is going to do is it is going to look in that table. It is going to grab an address, throw it in the code segment, and start executing. So that means we need a hardware level interface, and the hardware level interface we're going to use is x86 interrupt. Do you all know how hard it is to say x86 consistently in front of a class? First of all, 6 has an X in it, which is completely unnecessary, right? It could have been x85. That would be trivial. Okay, so let's set the stage a little bit for what a calling convention is. So usually when you call a function, it's not too bad because there's a lot of hand-holding going on. And that's good. Holding hands is productive. It's part of a well-balanced breakfast. And so when you're usually dealing with functions, what's going to happen is the compiler is going to set a bunch of things up before the function runs. The processor is going to be maintaining a bunch of things that are going to be consistent and be in expected states. The operating system is going to be maintaining some level of internal consistency. So you get to make a large number of assumptions when you start running a function. And you don't get to make any of those assumptions when you start running an interrupt handler because the interrupt handler could have been invoked by an operating system that's in some form of crisis. It could be running code that wasn't compiled. So we have to have some other form of calling convention. And we'll contrast this with easy mode. And easy mode is when the compiler just takes the call instruction. We don't have to think about the call instruction that much. The call instruction is almost sort of like reverse engineered for modern hardware from what historical programming languages did on less sophisticated hardware. But basically, every time you call a function, someone's going to set up a new stack frame for it and pass some arguments around. There's going to be some memory address written somewhere that you can return to, and there's going to be some expectation that when you return certain values are in certain registers. Right. Easy, super easy. But what happens when you have an interrupt? Well, you don't know whether you should be returning to the prior location. You don't know whether you have been provided with arguments. You don't know whether any arguments you've provided with that are potentially pointers are pointing to valid memory addresses. You can make none of these assumptions. And you can make none of these assumptions because any one of those things being wrong is what could cause an exception to take place in the first place. So everything can possibly be wrong. So how do we deal with this, not at the hardware level, but at the level of a programming language, is what we're trying to write? We're going to use the notion of a calling convention. But we're going to have a very minimal calling convention. So we are not going to use the x86 Linux system, and we don't know if it's V or 5, ABI, which is what is always used for C code. We don't get to use that. But I'm going to teach you a little bit about it because it's important anyways. Okay. So this is an aside on architecture and registers, and I totally have time to go through it. Okay. This is one of my favorite visuals on Wikipedia at all ever. I think it's a Wikipedia original. I don't know. This is how I understand the internals of the x86 processor. It is these registers. There's no way it's only these registers because there's hundreds of registers in x86, but there's quite a few here. This visually does a few nice things that I really like, which is it shows overlaps. And let's look at one case of overlap. I'm moving my mouse over EAX. EAX in my architecture class was the first register I learned about because it is the most commonly used 32-bit register. And usually when you're taking an architecture class, you're going to learn 32-bit first because your instructor took a 32-bit architecture class 20 years ago, and it doesn't make sense to update the slides. So what is going on here? Well, modern 64-bit languages like C, which is contrasted from Rust, which still uses 32 bits, is probably going to use the RAX register. Folks, no one knows what the R stands for. We just say it stands for register. It's not clear if that's true or not. E stands for extended because it is the 32-bit version of the 16-bit AX register. And there's little tiny registers in there. Those are 8-bit registers, AL and AH for the low and high subsets. But if you just look at this from the perspective of an 8-bit designer, way back in the olden days, you had 4 registers called A, B, C, and D. And then things got out of hand real quick, and now there's an RAX. But the RAX is not part of a collection of 4 general-purpose registers. No, there are many of them now. So you have A, B, C, D, H, 9, 10, 11, 12, 13, 14, 15, and then you have some special-purpose ones here, which is mostly, so we have the interrupt pointer and the stack pointer. Or not interrupt pointer, instruction pointer. Okay. This is pretty cool. We'll go over a few of these so you know them. Over here, top left, these are the vector registers over here. These things are big, and they were fast, and they mattered a lot before GPUs existed. This was the fastest way to do calculations. So if anyone has recently made you do an assignment in NumPy to practice your vector ops, this is what you were supposed to be learning. Now, of course, if you look at NumPy under the hood now, all that stuff's GPU accelerated, but we still pretend it's running on vector instructions. Like these registers that grew over time, so I think the Z prefix registers, my understanding is those are 512-bit registers, which is huge. That's a lot of bits for a register. Right. And when they initially built them, they had 256 and 128-bit registers. So the first vector instructions were only 128 bits in size. Now, you're thinking about this from the perspective of 2026, right? So a 128-bit register, that only holds 2 integers, right? So that's not a very good vector op. So, of course, they extended it to 512. Okay. These ones here, the ST0 and I think that's the MM0, right? Those are combined floating point and SIMD registers, single instruction, multiple data. Remember when we had to turn off SIMD, or BlogOS wanted us to. I don't have it turned off. The blog wanted us to turn off SIMD because, like, oh, it has, like, overhead costs or whatever. No one cares. Modern computers are fast, okay? Right? So we had to turn off SIMD for performance. And then that meant we also couldn't use floats. We already weren't using floats, right? Because who uses floats, right? Just write your own floats. Yeah, so on x86, they're the same registers. And, of course, this makes sense because you're probably doing parallel operations over floats. Right. I introduced these already. Instruction pointer, stack pointer. Oh, yeah, okay, over here, these ones are pretty interesting. I use these in my research. So over here we have a bunch of control registers. These things seem real poorly documented to me, and some of them matter a lot. Like CR4 has all kinds of stuff in it that's super important. Like if you change a single bit in CR4, like every single piece of code that runs on your computer will behave differently. Most of them aren't used by any individual processor, but all of them are used by some processor, which makes this additionally more complicated. But the control registers are very important for security applications. That's how I learned about them. And you'll never guess what's also important for security application? The debug registers, and they're important in a different way. The control registers determine what the processor should do, and the debug registers leak a bunch of information that's not supposed to be leaked out. So you're always panicking when you're a security engineer and anything shows up in the debug registers at all because you're like, who is currently debugging my processor? I'm visiting a web page, and it's like, oh, it's Bitcoin. Big Bitcoin is leaking your private key through the debug registers. So I always think of the debug registers as being, well, you've learned that I don't debug my code. So I only view debug registers as a security vulnerability. Back to work. Okay. Calling conventions. There are preserved registers. Okay, I have to take a step back. Under the standard functional calling convention, there are preserved registers. What are the preserved registers? The preserved registers are the registers that you can assume are not going to be fiddled with by whoever you call the function on, right? What does this mean? This means that when I am designing code and when I am writing my compiler, I can assume that if I hit a call instruction, my EAX or my ECX or my EDX are not going to be fiddled with by the called function. Now, that doesn't mean that the called function can't use those registers. All it means is that if the called function uses those, oh, I forgot we end at 40 and not 50. I will continue this unhinged rant on Wednesday. I'm very interested in calling conventions, so we will talk about this. I'm sorry I forgot how to tell time. Have a nice day. I really recommend watching Kingdom of Heaven.